Welcome to today's webinar with the title Proof of Reliability Using IST Part 2. The speaker of today's webinar is Mr. Dr. David Kurzmanowski, Technical Manager of our serial plant for Europe in Schopfheim. And now I wish you a lot of fun and new information.
Yeah, thank you, Mr. Schill. Hello, everyone, and welcome to our today's webinar. At first, we are going to start with a short introduction about PCB reliability and how to measure it. Next step will be the display of reliability results, which sounds quite boring, but is very important. Then we are going to talk about the influencing factors, and at the end, I will give you a short overview about the portfolio at Würth Elektronik of reliability-related service features. So what is reliability? The definition says reliability describes the ability of a system or component to function under stated conditions for a specified period of time. What does that mean for PCBs? For PCBs, it means that they should provide their electrical functions over the whole specified service life. And of course, we have also other functions that the PCB should provide, but in fact, as long as it works electrical, no one will ever take a look at it. What we ought to know is that that even flawless PCBs will fail after some time if they are exposed to temperature fluctuations. And it's shown in the graph below what the reason is. The reason is that you have PCBs consisting of different materials, of base materials, which consist of glass and epoxy resin, and you have copper. And those have different coefficients of thermal expansion. And if it's heated up, it leads to the effect that the base material is expanding more than the copper, and the copper is stretched, just like a paper clip that you are bending. This diagram visualizes the effect a little bit better. We have on the y-axis the expansion of the z-axis in micrometer, and at the x-axis we have the temperature. And as you can see, the copper expands over the whole temperature rate with a constant rate of roughly 17 ppm. The base material or base materials usually have a coefficient of thermal expansion about 30 to 50 ppm per Kelvin below the glass transition temperature, and above the glass transition temperature we usually have 200 to 300 ppm per Kelvin, and that leads to a huge difference in the expansion of the z-axis, and this leads to a huge stress in the copper. And just like a paper clip that you bend too often, the copper will break after a certain time if this happens too often. And the time, what is happening? Sorry. So, and the type of failures that can occur are, for example, metal fatigue, which can lead to barrel cracks. You can have interconnection separations, you can have corner cracks, micromedia separations, and so on and so on. Those effects are all related to the copper that gets stressed by the material. And how this looks in reality is shown in those images, where you can see, for example, a corner crack on the left, or an interconnect separation at the right, or just as so the barrel cracks, or a failure which is very hard to find, a separation between the target pad and the microvir, which is shown here, and which I will come back later. I'm sorry, something is wrong here. So, okay, let's go to the next point. How can one measure reliability? And as you can see, measure is written in quotation marks, and this is due to that you cannot measure reliability directly. this is not a deterministic attribute, and you cannot have a meter or a kilogram of reliability. That makes no sense. And therefore, you have to measure it indirectly. And this is done in a way that specimens are repeatedly exposed to strain until the predefined failure criteria is reached. And one such run with exposure to strain and relief of the strain is typically called a cycle. And the number of cycles that the specimens accomplish without reaching the failure criteria represent the gauge for the evaluation of the reliability. This is important because the certain number is not the reliability of PCB. No, this also makes no sense. It's a gauge for the evaluation. This means you have to compare it either to a specification or to another product or to another stack up or whatever, but this is very important to know. The test we are talking about is the IST test, and this test works with specific test coupons that are shown here on the left. Those test coupons can contain either one or more so-called power cycles. Those can consist of tracks and holes, or only tracks, or tracks and microvias, whatever you need, and are used to heat the coupon. And then you have 1 up to 3 sense cycles, and those represent the critical design of the PCB and can consist of through holes, microvias, tracks, whatever you need. And they represent, as I told you, the critical design, and those are measured constantly to see what happens during the test. And here you can see such a cycle, a temperature cycle in the IST, and you can see the time scale here is in seconds, which means that such a cycle is comparatively short, roughly about 5 minutes, which means that we can achieve 1,000 cycles in just 4 days, which is quite fast. Additionally, we can simulate the soldering cycles with this machine. So we do not need an extra soldering machine to test our specimen. We can do it with the IST. And those are called the precon cycles. And what happens during the test is that the resistance is monitored constantly. Yeah? And you can see here such a typical diagram. At the beginning, you have a little bit fuzzy resistance, which is due to crystallization effects of the copper. Then you have the stationary phase, and at the end, when the specimen is slowly beginning to develop metal fatigue, it's failing, and it goes faster and faster and faster until it fails. And the good thing is that failure doesn't mean total failure. It means reaching a failure criteria, which is very often 10% in resistance change. And it means our specimen is not totally failed, it still works, and we can easily now detect the failure due to that you have more heat where you have more resistance when you apply power on it, and therefore you can locate the place where it occurred very easily and identify the mode of failure, which is very helpful. The IST has a very, very good ability of detecting various types of failures, even those that are very hard to detect. And one example for this is the separation between the pad and the microvia, which is only visible when very well prepared as a very small thin line, but those thin line is in fact, if you analyze it by FIB, a real gap, and therefore an open, and your PCB is destroyed. And this is hard to find, for example, with the TCT, but with the IST, we can find those errors very fast. Yeah, and since the test is very fast and has a very good ability to detect failures, we at Würth Elektronik do not only use it for reliability tests, but also for monitoring the quality of production processes. For example, our plating, desmium, laser drilling processes. And you can see here such a test plan, which is done every week. And the test is so fierce that we can detect errors before they are so strong that they will affect our production. And we can detect errors before we have an effect of the production. And this is very helpful to sustain a good quality. Yeah, in a nutshell, the advantages and disadvantages of the IST, we have the short cycle times, we have the constant online measurement of the resistance, we have the automated stopping when reaching the failure criteria, we can simulate the soldering cycles, and we have a very effective error detection. We also have some disadvantages. On the one hand, you cannot test PCBs. You need those specific test coupons which represent critical designs of the PCB. That's very important because you need those special connections and those special cycles on the coupons to be able to perform the test. And the second one is that you cannot test below room temperature. But I wrote it in brackets because I believe it is not a real disadvantage. If you remember this diagram here and you would enlarge the slopes, you can see that the blue one will go at one point below the red one. Yes, of course. But this type of stress is a shrinkage and it will not add to the stress that is applied during the heating, which is stretching of the copper. Yeah? And on the other hand, you are way below TG, and therefore the effects are not that strong. And we have proven, due to a lot of testing, that the IST is extremely good in detecting errors, and it's way better than the standard TCT, which can go below 0 degrees, yeah, or below room temperature. So I don't consider this a disadvantage. Let's come to the display of reliability test results. As I told you, it sounds quite boring, but the best data is useless if you are not able to use it in a way that you can really work with it. Yeah. Then let's see what type of results we get from a temperature cycling test. Usually you have a number of specimens, and each specimen has a number of cycles that it reached, just like in this table. Yeah, you have all information you need in this table, but the lucidity is limited. And now imagine you would like to compare 2, 5, or 10 such test series with one another, and you would like to handle those tables. I think it's impossible. You would see nothing. So it's not very suitable to work with it. And therefore, we need a better option. And our preferred option is the Weibull distribution. Here you see an example of the Weibull distribution with the data of the table before. The Weibull distribution, in the Weibull distribution, both axes are logarithmic. You have the percent axis, which means percent of failed coupons, and you have the cycle axis, which just means the number of reached cycles till failure. And as you can see the data just on one view. But you also get two important parameters, which are the shape and the scale parameter. And the shape parameter refers to the type of the distribution, which is very important for later determining the root cause of failure or seeing if the root causes are the same. I will tell you later. In this diagram, it just means the inclination of the linear slope. This defines it. Yeah? And the second parameter we have is the scale parameter. The scale parameter indicates when 63.2% of the specimens failed. And it's called the characteristic lifetime. Yeah, and it's a good parameter for a fast comparison of different test series. It's quick and dirty, but for a fast overview, it's very suitable. Here, and here you have an example how good this works. We have a huge number of test coupons and we tested them with different temperatures. And as expected, the hotter you test, the earlier they will fail. Yeah, that's what you can see just within 1 second. And you can see how good it is to compare different test series. And then you have the scale parameter, which tells you that each increase by 20 degrees makes roughly a ratio of 3.5 in the reached number of cycles. And you also can see at the form parameter, but see very well by the inclination of the slopes, here, here, and here, that they are roughly the same. And this tells us that the acceleration which is created by the higher temperature, more acceleration of the test, is valid in this type of test, since we have roughly the same form parameter and the same inclination. Because if they would differ very much, like in this example, it would tell us that something is wrong. Maybe we have a different failure mechanism, whatever. But if we have very different shape parameters, it tells us that you cannot compare those test series. Either the stack up is so different that you get a different result, or, as for the example with the temperature you took is so high that you come into a different mechanism of destroying the PCB, and therefore you get a different result. And in that case, you should adjust either the stack up of the coupons or the test parameters. Otherwise, if you have such a result with the same test parameters, it proves that your examined specimens do not only have different reliabilities, but they also differ in the root cause of failure, which well can be, for example, the one specimens fail at the barrel and the others get an interconnect separation. And that is something you probably will see with a Weibull diagram and the shape parameter. And this shows us how important this is to have the data in a way that you can really work with it fast and good. Let's go to the influencing factors of reliability. The most important reliability factors are, on the one hand, the thermal expansion properties of the materials. And there we have the CTE in Z direction of copper and FR4 or base materials. And we also have, which is highlighted, the PCB thickness. Yeah, all those values are in ppm per Kelvin. And this means the higher my absolute PCB thickness, the higher my absolute expansion of the material and the bigger the strain that is induced into the copper. How big this effect really is, I will show you later, but it is huge, I can tell you. The next important thing is the sectional area of copper that is affected by the strain. Of course, the bigger the sectional area, the stronger the copper, the more it can withstand the strain. And this section area is defined by the diameter of the through holes and the copper thickness in the through holes. But please pay attention, a higher copper thickness does not necessarily lead to a higher reliability. Why this is so, I will tell you on the next page. But before, I will come to the most important parameter, the operating conditions. In the end, in the field, the reliability of your PCB is defined by the operating conditions. Yeah? The stress that is applied in the real world to the PCB, that will define its reliability. And since this is so important, you have to talk to us about those conditions so that we are able to design the perfect reliability test for you, because the test needs to be related to those conditions. Of course, it needs to be accelerated because we want results fast, but you cannot accelerate too much. I will show you on a later foil an example for this. But let's go to the fact why a higher copper thickness not necessarily means higher reliability. If I increase the layer thickness of the copper, my copper will become stronger and stronger and stronger, and the barrel of the PCB or of our holes will not be affected very much by the expansion of the surrounding base material. That's true. But if the copper thickness is too high and our barrel is too strong, we have another problem, because those barrels are made for connecting different layers to one another. They are attached to inner layer connections. And if my barrel is too strong, those inner layer connections are moved with the material and are ripped off the barrel. And then we have an opening and our PCB is destroyed. And this leads to the effect that the increase of the copper thickness leads to an increase of reliability to a certain point. And after that point, it will go down again. And what the optimum point is depending on the specific design, on the build-up, on the different layer connections, and so on and so on. So it has to be found out or tested for each stack up. Alone. That's how you have to do it, because no design is like the other. Let's come to the big influence of the PCB thickness. We had a test sample of 2 millimeters, and what we did is we created exactly same test samples, same stack up, same number of layers, and so on, but we just varied the core thickness to get slight difference in the coupon thickness, plus 10% and minus 10%, which means overall roughly 20% change in thickness. And if you now have a look at the scale parameter, you will see that this 20% change in thickness lead to a difference in reliability at a ratio of 3. So we have a huge impact of the thickness. The absolute, as I told you, the absolute stress at the end defines when the PCB will break. And you have to remember this is very important. If you have PCBs that are made of the same materials but have different thicknesses, you cannot expect them to have the same reliability. It's not possible. If you go further, if you go further down, let's say you decrease it to 0.5 millimeter. It's a quarter. We were not able to get the specimens to fail. So this number here for the scale is not real. It's even more than this 1500. So you can say the reliability is 10 or maybe even 20 times as high, just because you have a very thin PCB. And of course, it's the other way around. If you increase it, it will fail earlier and earlier and earlier. But there is something we can do about it. We are not helpless, because we still have different base materials. And just by choosing the right material, you also can, for example, change the reliability by a factor of 3. So ABC are just standard materials at Würth Elektronik. And for example, if you use high performance materials for radio frequency, just like a Rogers material or other ceramic materials, you can even reach 10 times or 20 times the reliability. So with the materials, we have a good tool to influence the reliability if it's needed. And now let's come to the most important points. Your test parameters need to match with the operating conditions of your PCB. You see here this image with the egg. It looks quite funny, but it shows the fact as it is. If you test too fierce, you will get a fried egg. And if you have this fried egg, you will never ever be able to reconstruct how the chicken would have looked like. And if you test too fierce and you get a different failure mechanism, for example, the results you create are useless. Just an example. We tested coupons and they already failed during the preconditioning, so during the soldering. And one could say, oh my God, those are so bad, those PCBs. They didn't even survive the soldering process. But if you took a closer look, you could see that it was a TG135 material, and we used 260 degrees lead-free soldering, which the material is not suitable for. And therefore, we destroyed the PCBs because the resin was spilled. And that's the real thing that happened. And if the PCB is used correctly in real life, that would never ever happen. Yeah? And therefore, your reliability result is, as I told you, absolutely useless. So it's very important for you to talk to us. What is the goal of your test? What are the operating conditions of your PCBs? What specifications do we have to fulfill? And then we can design a test so that the results you get are useful for you, that you can work with it. This is very important. So remember, the test has to fit the operating conditions. Very important, and talk to us. We can tell you, we can help you with the right test conditions. And just a hint, as I told you, the shape parameter is a good indicator. It's also in this case, if you accelerated a test too much, if you tested too fierce, you will have those different form parameters. And this is a good indicator that you did something wrong. So again, it shows you how important it is to display the data in those Weibull diagrams. Let's go to the last point to give you a short overview about the reliability portfolio or test portfolio of Würth Elektronik. Besides the IST, we also have the good old standard temperature cycling test. We also can do climatic storages, we can perform soldering tests, peel tests, we can determine the thermal expansion factors or the thermal material properties by TMA and DST testing. We can do CAF tests and so on and so on. The portfolio is big. Tell us what you need, tell us where you want to go, then we can tell you which tests are right for you, which we have to perform and how we have to perform it. This is especially for the IST, where we can verify, for example, different optimization changes like different materials, different stack ups. If you use custom materials or different copper thickness and so on, we can test it and then we can prove or show what works best. And also we are able to validate the reliability of a certain product if you need it. It would also be possible to do it for every lot or even for every PCB by using an IST coupon on every production panel. But please pay attention, it is possible, but it is potentially very expensive. So if it's really needed, we can do it, but keep in mind it might be expensive. Yeah, and now just draw the cycle back to the first webinar. In a nutshell, we can simulate your operation conditions. We can define the right test parameters if we know what you want. We can do an intensive monitoring. We can localize the weak spots. We can localize the failure mechanisms. We can give you statistics of all. And we can do adjustments, optimizations, and we can again then validate those recommendations. So again, talk to us, talk with our experts, and then we will find the right test for you. And with this, I'm at the end of my webinar, and thank you very much for your attention. And I am now open for your questions. Thank you.